Okay, guys, this is the practical of November 97, alternative A. Question number 1. You are required to determine which of the two bleachers is the better value for money. So you were given with solution of A1, which was a solution of made by diluting 25 centimeter cube of super clean in 250 centimeter cube of solution. So you should note here that Fa1 is a solution made by diluting. So it is a diluted solution. Be careful about the question at the end. If it asks you to calculate the concentration of Fa1, you need to be very careful because it was made by diluting. Fa2 is a solution made by diluting again. So be careful about those terms. It is a solution made by diluting 250 centimeter cube of the bleach, the second one, which is germ-free, to make 250 centimeter cube of solution. Fa3 is 0.02 molar solution of potassium manganate acidified and potassium manganate 7. Both bleachers use hydrogen peroxide as their active ingredient. Now, you should always know that potassium manganate can only be used in the presence of H+, that is sulfuric acid. And I gave many reasons why sulfuric acid is the acid to be used, why nitric and HCl are not acids that you can use. And don't forget that you can use an excess of H2SO4, that is about 3/4 test tube would be enough. So there is no need to measure the exact amount if there is a need to be. In experiment 1, you are to prepare 25 centimeter cube of Fa1 in a conical flask and to add about 10 centimeter cube of dilute sulfuric acid from a measuring cylinder, and then to titrate the solution with Fa3. Now, I'll give you quickly a small diagram, a small way by which you can understand what you're doing. A very small diagram. So if you are to take this to be super clean, so this is super clean. It says that 25 centimeter cube of super clean was diluted into 250 centimeter cube in a volumetric flask. And from this, you took 25 centimeter cube of super clean back, because if this is Fa1, so this is Fa1 concentrated, this is Fa1 dilute, and this is this Fa1 dilute, which you took, as you can see, from this. So if you look there, pipette 25 centimeter cube of Fa1. So this is what the diluted solution is. So you are to pipette this one, right? So you took 25 centimeter cube of this and you titrate this versus potassium manganate, which is acidified. So you titrate it versus manganate, MnO4 minus, right? Acidified, of course, right? And this becomes your titer value. This is 19.1 or 19 point something, right? And this is the flowchart. So our guide here is to start by calculating the number of moles here, number 1. Then number 2, to use our mole ratio to calculate number of moles here. Then to use mole ratio again. To use dilution factor to calculate number of moles here. Now I should remind you that number of mole in 250 and number of mole in 25, you can do it by proportion, or you can say simply that this value here is going to be 250 divided by 25. So number of mole in the third position would be number of mole in the second position here, here times 250 divided by 25. Once you have number of mole in 250, you are here. Now you calculate number of mole in 25 of super clean. Now remember that this is dilution, so those number of mole would be the same. I'm writing number 3 again to make sure that you understand that number 3 here and number 3 in the 250, they are the same. Now from the volume and the number of mole, you can now calculate the concentration of super clean, and this is what we're going to do in the next part. Okay, guys, this is back again the same paper, but this time without without any writing on it. And as you can see, I have corrected it to say that every time we need to have 2 decimal places. So please don't forget this. 2 decimal places every time, and even the final answer here should be 2 decimal places. And that the values were not accurate, unfortunately, because in our practical session, the accuracy is plus or minus 0.10 centimeter cube. So you need to cater for this in your practical classes. Don't forget that you need to titrate them so that the accuracy is plus or minus 0.10 centimeter cube. And whatever you have between, which is out of this range, will not be accepted by the examiner. So 20.10, 19.10, 19.3, there's a difference of plus or minus 0.20 centimeter cube. That's why the candidate did not obtain full marks here. Okay, this is part A now of the question paper. Let us try now to answer those questions. Calculate how many moles of manganate are there in the volume of Fe3. So let us take that volume to be 19.10 as the example before. Calculate the number of moles of manganate. So the answer would be 19.10 times the volume, which is times the concentration. Now in the question, concentration was 0.2 molar. So times 0.2 divided by 1,000. So that is the number of mole of potassium manganate. I'm using simply the formula N equals to Cv over 1,000, where N stands for the number of moles, C stands for concentration, and V for volume in centimeter cube. Given the half equations, now you know that when you are given a half equation, the way to add them is to make sure that their electrons are balanced. And there we have 2 electrons, there we have 2 electrons, and there we have 5 electrons. So to make sure that they are balanced, we multiply the first equation by 5 and the second equation by 2 to make them 10. Now if we add those 2 equations, we should be getting 5 moles of hydrogen peroxide is consuming 2 moles of manganate. So the mole ratio is 2 moles of manganate is consumed by 5 moles of hydrogen peroxide. Now that you know the number of moles of manganate above, you can calculate the number of moles of hydrogen peroxide to be the answer above, that is 19.1 times 0.02 divided by 1,000 multiplied by 5 divided by 2. So we have the number of moles of hydrogen peroxide in 25. Now, the next part of the calculation is a bit tricky because you are asked to calculate the concentration of super clean in mole per liters. Now, remember there were 2 dilution before, so you need to be very careful. The number of mole in 25 is 19.1 times 0.02 divided by 1,000 multiplied by 5 divided by 2. Remember that this is in 25. This is number of mole in 25. Now that 25 came from 250, remember. So in 250 we're going to have multiplied by 250 divided by 25. Now from here to there, it is the number of mole in 250, which is the same as number of mole in concentrated Fe1. So remember, why it's the same? Because when you dilute a solution, the number of mole won't change. So the blue one up to here, it is the number of mole in 250, or it is the number of mole present in the initial Fe1. Now remember, the volume of Fe1 was 25. So the concentration is, you multiply this by 1,000 and you divide it by 25. Of course, you can do it by ratio, but I have a quick way of doing it, and this is no more number of mole, but it turns out to be our concentration. So this is our concentration of hydrogen peroxide in superclean. You can plug this in a calculator and calculate it, and it will give you answer. Coming with the same question number 1, but experiment 2, we need to repeat it now. Experiment 2, we need to repeat it with the same methodology, but of course you have to use germ-free. That is the second solution of hydrogen peroxide that was provided, germ-free. Now you fill the burette and then you calculate the number of moles below in the same way. So number of mole here is going to be concentration for times volume divided by 1,000. The concentration being 0.02 molar multiplied by the titer value. Now let this titer value be 21 centimeter cube. Let it be 21 divided by 1,000. We have now our number of mole here. So this is now the number of mole of acidified potassium manganate in our burette reading. Okay, we're back again with this November 97. Now, I just told you that the concentration of manganate was 0.02 given in the question. But I told you that the titer value was 21. Actually, when I checked the values of the student, the titer value happened to be lesser than the first one. We took the first one to be 19 centimeter cube. So we're going to take the titer value to be 13 centimeter cube. So let the titer value be 13 centimeter cube. So calculate how many moles were there in the 25, were there in this 25 centimeter cube of solution. This is the value which is written down. It's the same thing, yeah. How many moles are we here? How many moles of potassium manganate are there? So the titer value is this time 13 centimeter cube and not 21. So we calculated back number of mole equals to concentration, which is 0.02 times 13 divided by 1,000. And this happens to be around 2.6 times 10 to the minus 4. Right? So please excuse me for 21 centimeter cube. We turn it back to 13 because I found that in experiment 2 the titer was smaller than in experiment 1. Okay, let us proceed now with the calculation. So calculate the number of mole of hydrogen peroxide in 25. This is our mole ratio. So number of mole in 25 would be the number of mole of manganate, which happens to be 2.6 times 10 to the minus 4 times 5 divided by 2. And this amounts to 6.5 times 10 to the minus 4. Remember that we took the titer value in that experiment to be 13 centimeter cube, and that the concentration of manganate is 0.02 molar. Calculate the concentration of in mole per dm cube of germ-free. Now remember again that germ-free was formed by first diluting 25 into 250, and then we took 25 back and we titrate and we use 13 centimeter cube of manganate. So if I were to put some values on them, this is the concentrated germ-free. This is the diluted germ-free, which is actually Fa4. And this is the value that we took, the pipetted value. And this is the titer value. Now, we found that the number of moles of manganate was 2 times 2.6 times 10 to the minus 4. We found that in 25 we had 6.5 times 10 to the minus 4. Now we need to calculate the number of mole in 250, and we're going to let it be the same number of mole in now the concentrated Fa4, that is the concentrated germ-free, and then we can calculate from the volume and the number of mole their concentration. So what is the number of mole in 250? That's 6.5 times 10 to the minus 4 times 250 divided by 25. Now we are at number of moles in 250. Now we need to calculate it back in 25 concentrated. That is the same in 25 concentrated. So this is number of mole in concentrated germ-free. Now, once we have the number of mole, the volume is 25, the concentration becomes 1,000 divided by 25. And that amounts to 0.26 molar. Calculate which bleach is the beaker value for money, is the better value for money, given that super clean cost about $2.8 per dm cube and germ-free cost about $2.5 per dm cube. So the best way to do this is to let the ratio be 1 for both of them, and look at, for $1, what would you buy more? Let's have it to be super clean. So super clean is 2 germ free. The price for germ free for super clean is $2.8. The price for germ free is $2.5. And with those price, you can buy a concentration for germ free. We calculated to be 2.6 molar. And that for super clean, we calculated before, it happens to be 0.382 molar. Now, the easiest way is to calculate for $1 how much concentration you can buy for both. Now, if you do it in this way, the concentration that you're getting more for $1 is more profitable for you. So if you take super clean, it means $2.8, $2.8, you are buying 0.382 molar. So $1 you would buy 0.382 over 2.8, and that amounts to 0.104. That amounts to, actually that's the other value. So that amounts to, the calculation is the same. That amounts to 0.136 molar. Same is true here for $2.5. You are buying a concentration of 0.26 molar. For $1, you would be buying 0.26 molar divided by $2.5, and this will amount to 0.104. Now it is clear. For $1, you are getting so much of concentrated. For $1, you are getting so much of concentrated. So which one is better? The better for money would be super clean. For $1, you are getting a high concentration. So that would be the best one. Okay, guys, question number 2. That is an assessment of planning a skill. You are provided with 150 centimeter cube of Fa4, 5, and 6, and you are to identify which of the solution would give the high, which of these solution is Fa1, Fa4, Fa5, and Fa6. So we don't know which one is which. You are provided with 3 colorless solution, 1 molar NaOH, 1 molar HCl, and 2 molar HCl. You are provided with a thermometer, a plastic cup, and measuring cylinders. The idea behind the practical is first to locate sodium hydroxide. And you can do it in practical classes by touching the solution. But remember, we don't have the right to write this in your answer. If you touch them, the one having a soapy feeling will be sodium hydroxide. And when you do it, you will come to know that it was Fa4. So right now we know that Fa4 is sodium hydroxide by having a soapy feeling. But as I'm telling you, you cannot write this in the final exam. It won't be accepted. But we have an idea. We know which one is sodium hydroxide. So this is sodium hydroxide. Now, which of the two would be Fa5, Fa6, 1 molar or 2 molar HCl? The idea is now to take mixtures of Fa4 and Fa5. Fa4 plus Fa5. Then Fa4 plus Fa6. Now, because both are acids and bases, both are going to be exothermic and both are going to have a temperature rise. Now, if you keep equal volumes of them, let's say, for example, you're going to take 50 centimeter cubes of Fa4 and you are going to add it with 50 centimeter cubes of Fa5. Because they have the same concentration, the one giving you the highest temperature rise out of those two mixture. So you are also taking 50 centimeter cube of Fa4. You are mixing it with 50 centimeter cube of Fa5, right? Oh, sorry. The second one is Fa6. you're taking equal volumes, you're mixing them. Remember, these concentrations are both, this one can be 1 molar or it can be 2 molar. But our sodium hydroxide is 1 molar. So the mixture that will give us the highest temperature here would be 1 molar NaOH plus 1 molar HCl. That will give us the highest temperature. If the volumes are equal, if the concentrations are equal, then we have the highest temperature. Now you are to perform the experiment. When you perform the experiment, you obtain two different temperature rise. I think that in this one, you obtain about 3.5 degree rise. And in this one, you obtain about 3 degree rise. Meaning that this Fa5, you obtain the highest temperature rise. So Fa5 is therefore 1 molar. By default, Fa6 is therefore 2 molar. And Fa4 is NaOH. So that is 1 molar HCl, that is 2 molar HCl. Now, what are you going to write in exam to explain the examiner that you identify NaOH? Now, you could say that when we added Fa5 and Fa6, there was no rise in temperature. Because the temperature didn't rise there, it means that they were both acids. And you concluded, therefore, that Fa4 was sodium hydroxide. Now you are to write the plan and the result. You can put it in a tabular form. I found that most of you, you wrote the answer in continuous writing. So it is better to put it in a tabular form and you can have the conclusion below. Coming now to your question number 3, that is the salt analysis. It was better than before. But still some of you fail to recognize some very important tests there. Add sodium carbonate. Now remember that sodium carbonate is used to test there. It is used to test. It is a test for H+. It is a test for Al3+. It is a test for Fe3+. It is a test for Cr3+. These are highly charged cations, so they are polarizing. When you add sodium carbonate to them, they would simply form carbon dioxide. This is what you're looking. You are looking for carbon dioxide, right? So wide open, their eyes wide open, looking for carbon dioxide. If you don't have carbon dioxide, if you don't have effervescence, if you don't have carbon dioxide, then you would say absence of carbon dioxide. Voila, absence. But if you do have effervescence, then you would conclude that yes, you've got carbon dioxide or you've got effervescence. And this is actually what happened in that practical. So if I were to quote from your answers, afterward I'll show you some papers, you got effervescence. You also tested the gas to be carbon dioxide. It turns the lime water milky. So your deduction would be presence of H+, possible presence of H+, Al3+, Fe3+, or Cr3+. These are the possible answers. You couldn't conclude anything else, like you got a like you got a precipitate or whatever. These will not be accepted because we're looking there for those. Now, if this effervescence did not occur, then we could say that those ions are not present. But for the moment, you got the effervescence, so they are present. Add barium chloride. So you know barium chloride allows you to identify sulfate and sulfite. So what I would say is, before you start your practical with a pencil, you could write the possible test like what I'm writing there. Then if it is observable, you write the answer. If it is not observable, you write the absence of. Because remember that you are to indicate, look at this, you should indicate clearly at which stage the test is occurring, writing any deduction you might alongside your observation. This is very important. Yes, with this one here, you obtain a white precipitate. No. You obtain, there was no visible change. So you would say absence of sulfate or sulfite. You add ammonia. Ammonia is a test for it is a test for cations. ammonia is classically to test for cations. So this is cations based on their precipitate, based on their color, based on their solubility, and so on. You got here a brown precipitate. So brown precipitate. So that could be Fe3 plus. Some of you said that it might be Mn2 plus. Okay, we can accept for the moment, but I do know that it should have been more of Fe than Mn. Filter, you obtain here a colorless filtrate, and you obtain a residue which is brown. Of course, that brown precipitate, I forgot to mention, it was insoluble in excess. Okay, let us try to see more. Remember that up to now we have a colorless filtrate on the page before, or we have also the formation of a brown precipitate that was insoluble in excess. To the filtrate, now we add nitric acid. The first thing here would be, to observe with nitric acid, because we should know that with nitric acid we can have an effervescence. If there is no effervescence, like you had here, no effervescence, then it means the absence of, so many times I'm repeating this, absence of carbonate, absence of sulfite, absence of nitrite. If it is a carbonate, you would have obtained a brisk effervescence, so that would have been brisk. If you have a sulfide, it would have been slow effervescence. And if it is a nitrite, it would have given you brown fumes. So no effervescence, absence of whatever I have mentioned above. Then you add silver nitrate. That silver nitrate is testing for halides, and actually you obtain a white precipitate. So if it is a white precipitate, it means that there is a possible presence of chloride, Cl-. It might also be a possible presence of bromide. I would understand that there is a difficulty to, at this moment, differentiate between white and cream. But when we add the ammonia, this is exactly what we're looking at. Add the ammonia to differentiate between the chloride and the bromide. The white precipitate dissolves. If it dissolves, then it is presence of Cl-, which is confirmed. Add sodium hydroxide. This is testing for cations. You get back again here a brown precipitate. And the brown precipitate was insoluble in excess, meaning that we get again the presence of Fe3+, which is confirmed. The next one now is to add hydrogen peroxide. Now, hydrogen peroxide is an oxidizing agent. So when we add it, it is going to test for reducing agent. In your syllabus, there are two main reducing agents. You need to learn them, Fe2+ and I-. With Fe2+, we're going to have effervescence and a gas evolve that relights a glowing split. Oxygen gas would be formed. With I-, the solution will become brown, because iodine is going to be formed. When you add hydrogen peroxide, there was no visible change, meaning that we have absence of Fe2+ and absence of I-. So what was there as a cation, Fe3+, what was there as an anion, Cl-. Now I can say for sure that most of you there, you found this part. Most of you got this. And here it was mistaken for most of you. It was a big mistake there. It was an absence of your ability to give the reasoning for hydrogen peroxide. And the remaining part was more or less okay. I'll show you some papers now of your friends so that you can know what are the mistakes there. Here you go again with some of your friends' results. You can see that these were properly written with some slight mistakes, like H+ was missing there. The barium chloride, there was no visible change, absence of the sulfate and the sulfide. The brown precipitate with aqueous ammonia showing the possible presence of Fe3, but I don't know why, possible presence of Cr3, Cu2 and Fe2. These are not brown precipitate insoluble in excess, so that was a mistake. Another mistake was that when you filter them, make sure at least some words should be there about the color of the filtrate or the color of the residue. That was also missing. Next, the white precipitate form. Yes, you could also have written nitric acid, no visible change, so absence of carbonate. But it was written there, white precipitate, but absence of carbonate, sulfites, and nitrite was missing there. But sulfite could be omitted here because we already said it before that sulfite was not present in the first part. Because when we add the barium nitrate, we didn't obtain any white precipitate absence of sulfite. We could still not write it here, but absence of nitrite would be there. You should have written it. And the dilute nitric acid, we should also be looking for effervescence that we never saw there. Right? You got a white precipitate which is soluble in ammonia that dissolves in the ammonia. Cl- is present, Cl- is confirmed. You add sodium hydroxide, you get a red brown precipitate. Now you do know that it is Fe3 plus, and I don't know why it was copper before. I don't know why it was Fe2 before. Filter the mixture, some missing parts there, color of the filtrate and color of the residue, and then add hydrogen peroxide, no visible change, and absence of I minus. Okay, I could also add absence of Fe2 plus, but I do understand that absence of I minus is a very good answer. Here you go, guys. Please correct your practical and make sure that if you have any question, let me know.